Alright, in this study we're going to do a linear elastic 2D beam model. We are importing our mesh and we're going to measure the geometric properties of that mesh, and we're going to look at the units which we're going to use this time, and we're going to run all the necessary parts to create a model and then to run it in Abaqus and see the results. So let's get to it. This is a new file here, so we're going to go to File, Import, Model, and import our mesh as a input file. Click OK. Right, so here it is. We can actually delete this other one here and go into this and maybe switch context here to see it. And let's start with, the first thing we're going to do is we're going to create a model. But before we can do that, we need to decide what units we're going to use. And here I have these units that you could use. You know, if you're using engineering units, you might use millimeters. Yeah. So in the visualization videos, I didn't use millimeters. I used meters, and that's the reason why everything was a little bit weird in the results. So let's do meters now and see where that takes us. First, let's measure the size of this thing. So we can go to Tools, Query, and take Distance, and then we're going to measure the length distance. So we can take these 2 points here, just to get a rough estimate of the length. So this is 100. All right, 100 times what? 100 times 10. So 100 long and 10 height. So let's decide now that we're going to use millimeters. So this thing is going to be 100 millimeters times 10 millimeters here. All right. So once we've done that, we can see here that our stress is going to be measured in megapascals. That's Newton per square millimeters. And take it from Wikipedia here that the steel stress, the Young's modulus for steel stress is 200 what? 200 gigapascals, right? So yeah, so let's use that. Materials, create, and we're going to I don't bother changing names so that you can, but I won't. Go into mechanical, elasticity, and let's create an elastic material. The type can be isotropic here, and now let's use 200, and yeah, let's go with 210, and then this is now in megapascals, right? And we need it to be gigapascals, so we just go E3 here, right? 200,000 megapascals. The Poisson's ratio is 0.3 in this case. So let me just tell you that you have to be very aware of what units you use. This is actually the second time I'm doing this video, because the last one I accidentally typed 210 and left it at that, and then I got huge displacements. So yeah, in order to fix that, just make sure that your units are consistent. So okay that, and let's create a section. So create a section name, just section 1. This is a solid and a homogeneous. Continue. This material is selected. Now the thickness will be left at yeah, we can change this to 10, but you know what, let's just leave it at 1. No, let's make it quadratic. Let's go with 10. Okay, so thickness is 10. Now we have to assign this section here to our model. So go to section assignment, create, and we need to select the region. Let's do that, and then click OK. We're done. And then it automatically found that we have, hey, you just have one section, just select that one and assign that, and that's it. So we have that. Now we know that our mesh, which we can actually query it here, query mesh and select the entire thing and press done. You can see here that we have 250 linear quadratic element of type CPE4. If we didn't have that, if our input file didn't say that, then we would need to go to mesh. We can do it. It's not, and nothing's gonna happen really. We can go to our mesh. We can click on assign element type. We can select this whole thing, and we can click done. And it's going to say that okay, that you have a standard plane strain linear element CPE4. It already says that. So we can change this. Of course, you can say that you know what, I want plane stress here. So you can do that. We can reduce the integration, but we cannot go to quadratic here because we don't have these. We don't have these extra nodes. All right, so let's just stick with this plane strain and linear, and okay, or cancel. Didn't really do anything. All right, so once that is done, we can go to assembly. We need to create assembly. So switch context here, go to this button here, create instance, and create a part. That's it, because we only have one part. That's enough. Now steps. In a linear elastic model, this is quite easy. Not too many parts to it. We create a step 1, continue, and all of this is just left alone because we're not going to, it's not nonlinear in any way, and we don't need to iterate through anything. We can just leave it as is. Okay, so field request output. Let's see here. We really can't use a history output because it's not going to iterate, so we can actually just delete this. And then in the field output, remember all of these that we select here are going to be computed once we get the solution field, the displacements. So contact, don't need them, don't have them. Energies, well, we don't really need that. Reaction forces, sure. Concentration forces, moments, yeah, those are given really, so those are not computed. But in here we have the strains are going to be computed, and we know that we're not using any plastic model, so we can remove that, remove this. I'm not really sure if it actually, if it sees that if Abaqus sees that we don't have a plastic model, plastic material, maybe it doesn't even compute this. I'm not sure. This happens really fast anyway, so it doesn't really matter if you have this selected or not. For this particular study, of course, if it gets bigger than the time it takes to calculate this could be significant. So yeah, let's leave it at that and press OK. All right, now we need to create loads. Create. It's a concentrated load or force, and continue, and we have to click. We can select this node here, or we can select the sets here and click on the load here, because we have created this manually in MATLAB already. It's highlighted to see that it is selected, right? And then do it in the Y direction, CF2, and put negative 100 newtons. It's probably enough to start with. Okay, and then boundary conditions. We can go with symmetric, antisymmetric, encast, and click continue. Click boundary conditions, make sure that they light up. Click continue, and then see here, down here, all of these U1 is equal to U2 is equal to U3 is equal to UR1. That's the rotational around the x-axis, y-axis, and z-axis. So all 6 degrees of freedom are 0. So click that. And once that is done, we have our model. So now is a good time to save this. Linear elastic beam. All right, yes, in my case. Now we need to create the actual job. So right click on jobs, click create, and the source is our model, and the model name is mesh. Click continue, and nothing to worry about here, just click OK. So now it is created. We can create lots of jobs and then we can run them. So right click job 1 now and click submit, and there's a job file already. Do you wish to continue? Yes. And the history output is not requested. Do you wish to continue? Yes. So it's submitted. We can view it. We can go to monitor, and you can see here that the analysis input file processor started. What Abaqus does once we create this job is it creates an input file with all of the model, including the mesh. Everything is in there, and then it sends it off and says, you know what, solve this. And then the Abaqus solver, called standard or explicit depending on it's starting, and it goes really fast. It's already done, completed. It's one increment and one time step, and that's it. So we can close this down. Once it's completed, we can right click it and go to results. Yeah, now I have two jobs here. Double click your job, which is job 1 ODB probably, and click plot continuous here. The scale factor is set to 1, and now we can see here that we have this is set to engineering notation. So you can see here we have 24 to the power of 0, so this is 24 megapascals, right? Newtons per millimeter squared. So the maximum is 24 here. Yeah, and we can change this to the displacement, so we can see that we have some, this is millimeters, right? So 87 micrometers is the displacement. So the load was pretty low. All right, so yeah, we can take a look at the XY data here. Go to continue, go to unique nodal U2. All right, so go here, select that node. Select, and press done, and node 1 is selected, and plot. And we can see it here, displacement is going down to 0.08 or 9 something millimeters at the full load applied over here. Okay, so that's a basic linear elastic problem done in Abaqus. Nothing special to it. Next, we will look at what happens if we increase the load too much. All right, so that's it. See you in the next video.